GIS and remote sensing. I'm a GIS and remote sensing graduate, and I'm also interested in the challenge. I'm waiting to learn more about it. Thank you. It's my first time to do a Zindi challenge.
Awesome, welcome. So my name is Amy Bray. I'm a data scientist at Zindi, and I set up the competitions. I'm going to share my screen soon to show the challenge. If you've got any questions, please post them in the discussion. The way this webinar is going to work, I'm going to walk through the challenge, thank our sponsors, and then introduce Magdalena, who will be walking through the starter notebook. The floor will then be open for questions that Magdalena can answer. So this is the NASA Harvest Field Boundary Detection Challenge. This is quite an exciting challenge. It has been in the pipeline for 2 years now. We started working with the University of Maryland 2 years ago, who are working with the government of Rwanda. So we are so glad to have this on Zindi, and this is going to be a competition with real impact. So small farms, less than 2 hectares, these are farms that you often drive past on the road, produce 35% of the world's food, and mostly found in low to middle income countries. This challenge is to detect the field boundaries for these tiny farms in Rwanda to help contribute towards food security in Rwanda. We want to say thank you to the USDA Foreign Agricultural Services and USAID for sponsoring this challenge, as well as supporting with data collection and finding stuff. I'd also like to thank the University of Maryland and NASA Harvest. They've been working on this, I think, for 3 years now, and we've been part of it for 2 years, and Radiant Earth has jumped on this year. So it's been a real worldwide collaboration. And then Radiant Earth for finding out about this challenge. I think you heard about it at a conference on Earth observation and you're really interested and decided to get on. Radiant Earth helped with data labeling and hosting this on MLHub, where you'll be able to find all the data. The evaluation for this section, for this competition, is the F1 score. Magdalena will show you how to create a submission file and what to consider with an F1 score. Prizes, we've got $5,000
Something happened. We cannot hear you.
Amy?
Hello?
I think she must have lost connectivity. there must be an issue with Amy's connectivity. I was trying to see if I could share my screen, but she has it disabled, so I cannot share my screen. I apologize. She's having some technical issues. She's trying to log in from her phone now. Please, hopefully we'll sort it out soon. I can't even. So I'm gonna go through the starter notebook that has all the instructions on how to get to the data and all of that. But I can't do it until she gets back on because she needs to allow me to share my screen. And I won't be able to do it unless she unlocks this thing. I hope that she can get back on and we can sort it out.
Hi, Magdalena. I've just joined again. I was kicked out with my Wi-Fi. Have you started sharing the notebook yet?
No, because I wasn't able to share my screen. Sharing is disabled.
I know. Okay.
I'm in South Africa and we have load shedding at the moment. I think like scheduled power outages, and I thought I was prepared, but apparently not.
Oh my goodness. I'm getting host disabled participant screen sharing.
Try now.
There we go.
Awesome. Over to you. Thank you everyone for dealing.
Okay. Hello, everybody. I'm Magdalena Benza. I'm the lead geospatial data scientist at Radiant Earth Foundation. And what we do at Radiant Earth Foundation is we collect, curate, and host training data sets for machine learning applications with Earth observation data. And so the data set that you're going to be using for this competition is a data set that we helped generate and curate and are hosting now in our Radiant MLHub. And so I'm going to go over this starter notebook. It has the baseline model for this competition, and it has some details on how to access the data. And I can tell you a little bit more about the data, and you can also feel free to ask questions about the data sets as we go. See this baseline model, we have it on, I believe the GitHub repo has both Google Colab and just a regular notebook that you can run on your own computers. But I'm going to go over the Google Colab that has, it's the same model. So the first thing you need to do is to install all the dependencies for this to be able to run. We have a requirements text file in the repo that has everything you need to be able to run this. Then you're going to import all the libraries you need. And then you're going to go on to download the data sets. So in order to get access to this data set, you're going to have to create an account at Radiant MLHub, and I believe the instructions are on the competition's website. It's super easy. You just need to create a user name and create an account. It's free. It just gives you access to all of our data sets, and they're all free and available for developing models. So once you create that account, you're going to go into Radiant MLHub website and go into your account settings and copy your API key, and you're going to paste that API key into this cell in order to get access to Radiant MLHub and get to the actual data set. So once you paste that API key, you can download the data set. And I've already run this, and I just wanted to show you what it looks like. So you're downloading 3 collections, source strain, source test, and label strain. And this is what it looks like. So when it first downloads the data sets, they come into these tar.gzs and they get unzipped into these 3 folders. And so the train data has all of the labels, and these are basically the field boundaries for this for these competition. So, and I guess we didn't really explain much about the actual data set because of all of the technical issues. So this data set was created using Planet satellite imagery from their NICFI base map data set. These are satellite images at 3.7 meter spatial resolution. And so we use those data sets to label field boundaries and for a few regions in Rwanda. And so these were annotated by a team of annotators, a company called Takadam. And so they used 3 timestamps. So they had access to that same chip for 3 different timestamps, and they were able to look at how the field looked like in March, April, or August. Within that chip, anything that looked like a field, they would draw a boundary around it. And so that's how we generated these labels. And those and we are only interested on the boundaries. We're not interested in the actual field areas, just the boundaries. And that's how we've generated those labels. And so those labels are then converted into these raster labels. And we have 70 chips for label data and paired basically to this planet satellite imagery that we want to use for the model development. So we have the labels, then we have the source test and the source train. And so for the source train, you're going to have basically all of the imagery that is the satellite imagery that is available to use as inputs for the model development. And so for each one of those chips or tiles that we've created, there's 70 in total. You're going to have actually 6 timestamps. So for example, if you see here for tile 00, you have March, April, August, October, November, and December. And so for each one of those chips, you're going to have 6 different timestamps from that planet imagery available. And so this is what's available on the source train. The data set has been basically split. So there are, I believe, 57 tiles in the train data set and 13 in the test. So for the test data, you're going to get the same 6 timestamps for each one of those 13 tiles, but you don't have the labels, right? So what we need is for you to predict the labels for those 13 tiles that are in the source test data set. I hope this is clear. I haven't confused anybody, but if you have any questions, please let me know. I also apologize, I'm recovering from the flu, so I might start coughing anytime soon. Anyway, so those are the 3 collections you can download from this data set. The tiles are 256 by 256 by 4 bands. This is
Just
again.
a quick question.
Yes.
Are the datasets in raster format, all of them?
Yes, they're all in raster formats, the imagery and the labels, and they're all aligned and tiled, so everything is just pre-processed and ready to use.
Okay, thank you.
So as I mentioned, the imagery is planet imagery from their NICFI program. The NICFI program is a program that they've, I believe they're working with, is it the Norwegian government? They've put together basically a large series of base maps, monthly composites that are free to use for research that is involved in sustainability issues in tropical areas. And so this is how we got access to this data set. And so these are base maps. It means that they're image composites. What they do is for an entire month, all of the satellite imagery that is collected for that month, they find the best pixels, the ones that have the fewer clouds and whatnot, and they pick always the best representative pixel for that month. And so that's where you get an image product that might be might have less clouds and might not need so much processing. And so that's what we're dealing with. We have one image for each month, and in this case we have 6 months available: March, April, August, October, November, and December. And so this will allow us to look at fields during the on-season and off-season. So we should be able to see how they look when there are crops on the ground, and how they look when there are no crops on the ground. And that should help us delineate field boundaries. So here we're just pulling the file IDs from source train and label train, kind of just cleaning up the strings a little bit, because as I showed you, it's the names are really long because it includes the tile number and the actual date. And so that will give us a way of kind of tapping into both the file number and also which one of the timestamps we're working with. Once we have that data, this is a function to normalize the imagery. Just very simple normalization. And then for this particular model, and I just wanted to mention, this is a model that was developed by our data scientist at Radiant Earth Foundation, Daniel Nueze, and he's worked on field boundary detection models for a while. He's actually written a blog post about a very similar model. So he applied here some data augmentation. This is because our data set is fairly small. We only have 70 chips in total. So he had been looking into maybe using some data augmentation to basically improve the models with more data sets. So let me see. So he has here a bunch of functions to apply this data augmentation, rotation, flip, blur, and I'm going to show you real quick what it looks like. So this is what the paired data set looks like. This is a false color image. As I mentioned, the satellite imagery has 4 bands. So it's red, green, blue, and near infrared. In this case, this false color image is using the near infrared, red, and green. What this band combination does is it really highlights vegetation. So everything that is red here is vegetation. I know it's a little counterintuitive because it doesn't look green, but it actually near infrared band really picks up on the vegetation, and so we've used false color composites here to showcase the vegetation here. And so on the right side you have what the actual field boundaries look like. So this is what we need you to predict. This is the original tile, and this is how it looks like after going through the data augmentation piece, in this case using rotation, flipping, and blurring. So just padding our data set to make it a little larger so that we have more data points to run the model on. There's a couple of functions basically to just generate the data augmentation and apply it to all of our data set. Very simple. And then in the end, just loading everything up into a large array with our X's and Y's, all of the satellite imagery and all of the timestamps and all of the masks for the field boundaries go in there. So that's that for the data prep for this piece. And again, we decided to use data augmentation for this baseline model. You don't have to. You can develop your own data augmentation if you want to. This is something that we have used in the past, and so we decided to use it here. In terms of the actual model, we used a UNet model with a ResNet 34 backbone, and so this is again what we've used here, and you can basically pick whatever approach you see fit for this. So we have here the actual UNet model that we kind of tweaked for our input sizes, and the learning rate scheduler, number of channels, input shape. And so this is something else that you're totally welcome to tweak is we used all of the 6 timestamps in the model, but you're welcome to decide to use fewer timestamps if you want. You can test and see if there are some timestamps that might not be needed. We are using recall and F1. So we're defining those in a couple of functions here too. And basically just building the model here, loading the backbone and the metrics. And that's pretty much it. And then running the model. So once the model is run, you can save it and run it for the test chips and generate. So here we're basically loading the test chips and generating an array for those and generating predictions. And so the one thing that we have here is the predictions are basically arrays of those field boundary masks. And in the end, what we need is to convert those field boundary masks into data frames that we can load into and convert into this submission file. And so there's here these 2 functions, or actually these 2 cells help us turn that, or actually this cell, turn that into what's going to be our submission file, is converting each one of those tiles, predicted tile masks, into data frames. We're flattening it and converting it into the submission file and that's it. I think I went pretty fast over everything. If anybody has any specific questions, I'm happy to answer.
Thanks, Magdalena. I think you did really well with that code. We've got a question from Katie Magar. What is the difference between chip tiles and then timestamps? I think you're using chips and tiles interchangeably, but I'm not a geospatial person, so maybe you can talk to that.
Yes, so I am using chips and tiles are the same thing. So basically, there are 70. This is what a paired chip or tile looks like. So you have on the left side the imagery, on the right side you have the labels, right? And so we have actually for each one of those 70 tiles, what we have is 6 timestamps. So there's an image for March, April, August, October, November, and December. So there's going to be six timestamps, 6 images for what, and what I'm showing here on the left side is just one timestamp, but there are actually 6 available, right? And there will be just one field boundary raster label that is paired to that. So there's 6 timestamps paired to one field boundary label raster. And each one of those 6 timestamps has actually 4 bands. So it's 6 times 4. So it's 24. I don't know if it makes sense.
And those timestamps are from different seasons of the year. So we've got April and May, which would be the harvest season, and then again August, which I think is the planting season. So you can see. I do not have a good article, but maybe someone else can share more in depth on the different ways of chips and tiles. And I've seen some really amazing magic happen where you combine the different bands, as Magdalena here busy highlighting the near infrared band. But I know combining different bands brings out different features. We have a question from Claudia. How do you generate close crop boundaries? Do you apply some post-processing step to the output of the deep learning model?
So you are welcome to do that. We have not done that. That is something that is normally done for field boundary detection models. I mean, you're welcome to do it. I mean, it's just we haven't done that. But in the end, you do want the prediction to be a raster, and so you want even if you do some post-processing, I mean, I would say that normally for field boundaries, you would do it as a vector. You wouldn't need to then convert like back into a raster for the submission. But yeah, no, we haven't done any post-processing.
So you mean the submissions will be...
eCognition folks. This is Keith Peterson, the eCognition product manager from Trimble.
Hi. Did you have a question?
Yes, I had a question.
Mm-hmm.
And you said the submission, do you want them to be a raster or a vector, or do you want the whole code, or what should be the output be?
So the submission is actually, so the output of the model in this case, it's a series of arrays, right? So you're predicting, what you're doing is you're predicting a raster mask with the field boundaries, and you have to turn that into, you have to flatten it and turn it into a data frame, and that's what's going to go into the actual submission file. So it's going to be a flattened array that is going to be turned into a data frame, and that's a submission file. So it would have to be a raster that becomes this flattened array.
Okay,
We've got some more questions. Oh, Brian, do you have a second question?
Okay, my other question was like the submit. Do you need the whole script created, or just the outputs, like the detected fields that you need?
So maybe I can talk to this. So what you're going to do is you're going to log on to Zindi, sign up to MLHub, run this notebook. If you feel that you are a pro and you don't need this notebook, then I encourage you to go off and create your own notebook. Then you will need to flatten the array at the bottom and create a submission CSV file. And you'll just be submitting that CSV file onto Zindi. I think you can make 300 submissions up until the 26th of February, so you can submit 300 different CSV files. If you are in the top 5 of the leaderboard at the end, we will email you requesting your code, and then you would need to submit all your code like this. And once it's passed verification, there are some additional steps that you need to format it in a specific way, and that will be communicated afterwards. And that code will then be hosted on MLHub for others to add and to learn from your work.
Okay, thank you.
We have a question from Ismail. There are 6 timestamps. Are they from different years or are they from the same year?
They're all from the same year, from 2021, right? I want to make sure I have it right. 2021, yes. So they're all from the same year. The idea is to capture crops throughout the growing season and even during the off season, right? So it's supposed to be representative of the 1 year.
Thanks. We have a question from Lisa. No, we've got one above from Ala. Are there any limitations to what processes or techniques we can use? From Zindi's side, no, you can go as big as you want. We recommend not going too big because then it does become a bit heavy and a bit crazy and that you're throwing it into a black box, which we don't ever recommend. But Magdalena, do you have any restrictions or limitations?
So there's one thing that I believe we have in the rules is that we don't want people to use actual absolute coordinates as features. We want these models to be, so we want to be able to replicate these models, like if be able to run them anywhere. And the idea is that we don't want the actual lat longs to be features. We want you to use the features from the satellite imagery. You can do as much processing you want with the satellite imagery, but we request that you do not use lat longs as one of your features in those models. And I believe it's spelled out in the rules too.
Thanks for highlighting that. Again, from Lisa, are we to test out different models for prediction? Yes, you can. As I said, you've got 300 submissions, so you can test out different models, and then the best one you can select to be scored on to place on the final leaderboard. From Gideon, is the submission a binary raster, 0-1 values? Correct. So it would be 0 for the black in that image and then 1 for the white lines. Procuria, how are precision and recall calculated here? If you go onto Magdalena, you can maybe talk about it on the notebook, but on Zindi, we have spelled out how the recall is calculated, and the precision is just a subset of recall, of that recall metric.
So I have it here, but I don't think I only have, but it is detailed in the Zindi's competition website. I had it here somewhere too.
We've got a question from P while you're busy searching. Do the crops vary in different seasons? What are your findings? I think we're going to leave that question up to you to figure out. I think in the fallow seasons, everything would just be brown, so it'll be really difficult to detect crop boundaries, but it's really important. So good luck with that. From Filippo, no, you cannot use external or additional data for training, but a ResNet model was used, so you are allowed to use packages, just no additional training data, please. From Felipe. Yes, thanks for highlighting the evaluation, Felipe. Another question, would it be possible to recreate the source imagery from the original NICFI mosaics?
I don't know if I understand the question.
So in case additional reproducible pre-processing steps are needed, that cannot be done on the 256 chip. I don't think so.
So, I mean, those those NICFI base maps are just base maps, right? So we don't have the actual. So you're talking about. I guess you mean the imagery that is part of the base map. I'm not sure if I understand the question.
Yeah, sorry. So the question is if we would kind of think about performing an additional pre-processing to improve the quality of the images, but like in some cases you cannot do that on the 256 image chips. For instance, georectification, these things, right?
Yeah.
Could I do it on the original data and then recreate these image chips and use them for prediction, or is that considered not possible?
I mean, I guess. I don't know. That's a good question. How would you get access to the actual?
Oh, you can access them through the Planet API, right? So I could just download the original data that you provide here and kind of recreate. But sorry, it's a tricky question. You don't have to.
Yeah, no, it's a tricky question. I think we would rather that you use what the data set as we've just prepared it.
Yep.
The only thing we've done is basically just clipped it and just tiled it. That's all. That's all we've done, really. There's no. I mean, if you're gonna go and download the original base map data set, it's gonna be just the same. So I don't think there's any difference. But I would say, since we don't want any, since their general rule is no other data, then I would say let's just stick to the data set that we've provided.
All right, thank you.
I think it'll also be a mean feat trying to match the tiles we have on Zindi across the whole of Rwanda. So a question from Julius, can I share my GitHub notebooks with my peer network publicly? Yes, you can. So if you, please don't share any code outside of a team. Just that.
Amy, you're breaking up a little bit.
It's considered bad practice. But not against the rules. If you are number 10 and you share your notebook at the very end of the competition, like a week to go, how to access the
This meeting is being recorded.
Oh no, I think I dropped off again. We had a question from Jonathan. You mentioned that we cannot use additional training data. Archery, Bray networks and models, those are allowed. There was a ResNet model used here, so you're welcome to use that. How to access the data? What you need to do is you need to sign up onto the Zindi platform and search the NASA Harvest competition. I'm going to drop the link. And in the data tab, you can see all the instructions on how to sign up MLHub and access the data and access the notebook.
If you follow the steps here, and that's the first part of the notebook, there's an example of how to get to the data set too. You just need to make sure you have access to a user so that you can get an MLHub API key to paste here.
Right, let me just repeat my answer to Julius's question. So yes, you can share your notebooks and it's encouraged as long as you share them while competitions open with everyone, either on the discussion forum or on a very public channel. It is considered bad form or bad practice to share your solution if you're in the top 10 or the top whatever, and you decide to share your solution on the leaderboard, on the discussion forum. It means everyone else can come and copy paste your work, which in a way discredits the amount of hard work everyone else has put into their models. So it's not against the rules, but just bad practice to share a notebook like a week or 10 days before the close of the challenge. But once the challenge is closed, we really encourage you to share your notebooks on the discussion forum and on other public channels so we can learn from each other. Are we modifying the existing notebook or creating a new notebook? You can take this notebook that Magdalena is sharing at the moment, and it's also found on MLHub, and you can use this as a starting point. But if you feel comfortable to go ahead and create a notebook from scratch, then we encourage you to do that. Can one pre-train their models using other satellite images? Good question. I think not. No. You can use the data augmentation techniques Magdalena shared to increase this data set size.
So the thing with this planet imagery is that it's pretty high spatial resolution, and given the size of these fields, I mean, I know some other satellite imagery will have probably other data, but it's going to be a lot coarser, right? And so, yeah, in any case, believe we're sticking to the data sets we have.
Hello, do you hear me?
Yes, go ahead.
Yes.
First of all, thank you, Magdalena, for your presentation. It was so interesting. But I have a question for Ami. I just want to make sure that the test public and private split was done with group K-fold. So else, the public.
I think it was, but I will double check.
Yeah, please check it, Ami, because it would be not meaningful to split randomly the test. And thank you.
Is there a minimum or maximum result submission in this hackathon? There's no, the best result is to get a perfect score up to 1. So you're trying to maximize your result, but you can make 300 submissions over the course of the hackathon trying to get the best score. I'm going to start wrapping the webinar up here, but you can keep posting questions in the chat and we'll respond with text at the end. I just want to say thank you to Magdalena, who has led an amazing webinar, and has done an amazing job with the starter notebook, and she was project manager on this project, getting it up and running for the Zindi, which is just amazing. So thank you to that. Thank you for all the questions and for staying to the very end. This recording will be posted tomorrow afternoon on the competition page. So if you want to re-watch or reiterate anything, it's here. I just want to remind everyone that we all started somewhere. So this is your first Earth observation challenge or project, or it's your 100th. Please really engage on the challenge on the discussion board, asking for help or offering help. Good luck, everyone.
Thank you.